All right, welcome everyone. Thank you for joining me in today's video. Today we are looking at introduction to zero knowledge proofs, and we'll be looking at introduction to zero knowledge and then introduction to zk-SNARKs as well as zk-STARKS. I have been geeking over this topic for the last couple weeks and it's been mind-blowing. I've loved every single bit of it. The last time I was really excited about a piece of technology as far as crypto and the blockchain was concerned was a couple years ago when NFT started getting mainstream. And again, I buried my head into it. I researched and I watched videos and I just looked up as many things as I possibly could. And here I am doing something very similar with zero knowledge, except this time though I am trying to educate as many people as I can because it's a very interesting topic and I love it and I'm enthusiastic about it, and I want to give you a very high level definition and explanation about the concept just so it gets the gears rolling, because it was the same thing it did for me once I got an idea of how the architecture worked and how the entire thing worked. Not the math though, I haven't gotten very deep into the math yet, but the entire theoretical concept is very, very cool, and I have been able to draw and come up with a handful of very fun examples that further drive the point home. And we'll be talking about those in subsequent videos. So if that excites you, please give this video a like and then subscribe just so you do not miss out on all of that cool stuff. So I will put up my slides up here real quick so we can just dive into it. Again, super fun topic, super excited to get into it. So we're looking at intro to zero knowledge proofs, intro to zero knowledge SNARKs, intro to zero knowledge STARKS, the difference between both of those, why do we need zero knowledge, and we'll be looking at the folks that are building with / on zero knowledge as well. So what is a zero knowledge proof? Again, straight to the point with all of this. A zero knowledge proof with this really clear, concise example from Lean the Bin. I really, really love this example and this definition rather. It says the ability to prove honest computation without revealing imputes. So essentially, I'm proving to you that something is true without telling you, without telling you anything else about that except that it's true, but it is honest. So that is also a key word there to pay attention to. Honest computation, because there are fraudulent computations that could happen, and that is where some form of security is done, and which is the cool thing about zero knowledge. It is cryptographically proven. That is a lot of math, and math is as true as it gets as long as the problem sets are unique to every single individual, every single prover that needs to solve those problems. Again, a handful of this will be clarified in subsequent videos that I will be making, but what you need to pay attention to is the fact that you can prove an honest computation without revealing the input of those computation. Next thing, so this is another definition I found just because a lot more will be handy with understanding this concept. A zero knowledge proof is a cryptographic proof that allows one party to prove it possesses certain information without revealing that information. Again, very similar to the first one. I get to prove that I know something without revealing what exactly that thing is. So this is where, as you can tell, the consistent theme here is some form of privacy, right? So I don't tell you a lot of what you don't need to know. I only give you what you need to know. So to further drive the point home, we'll be looking at an example, but subsequent examples will be given and will be shown in subsequent videos. I have a video that is specific to talking about examples and use cases and theoretical scenarios as to how zero knowledge is very useful, and I'm super excited about those because while I was studying and researching and learning about zero knowledge, I thought about all of these use cases, and that's really cool. So I'm excited to start getting into those. But today we're looking at the infamous where is Waldo example. So where is Waldo zero knowledge proof example? So this is a very cool one. So right here we have this canvas of an image with a handful of people, and we're supposed to find someone called Waldo. Waldo is fairly unique as is everyone here, but we're supposed to find him and bring him to light, and that's what we'll be doing. However, though, to prove to you that Waldo is here, if I'm going to do that, I cannot just show you where Waldo is in this image. I can't do that. So we can assume that I make a living off of telling people where Waldo is without showing them where Waldo is, or telling people that I know where Waldo is without showing them where Waldo is. And if I were to point out to where Waldo exists in this image, I will technically be giving off the leverage I have, and anyone can then go ahead and, make a living off of that. Let's assume I want to monopolize the knowledge of where Waldo exists in this image. So if I were to show you where Waldo is right off the bat here, I am jeopardizing my source of livelihood. So to avoid doing that, we do something like this. I then take a yellow plain background and then I move this image around. I move it around, I just play with it and I move it around. And then in this yellow background, I find Waldo because I know where he is. And then I cut him out of this image and then I show it to you and like, yo, Waldo, here's Waldo. And they're like, okay, cool. Now that you've proven to me that Waldo exists here, we can proceed to the next step. Again, say I needed to get payments to prove to you that I know where Waldo is without showing you where Waldo is. This proof settles that because it is honest and I have not revealed to you anything more than you need to know. So that is zero knowledge. You don't know where exactly Waldo is. You just know that Waldo is here. And that is really cool, right? So basically, I haven't shown you where Waldo is, but Waldo exists here. But again, because this is an example that I want to, and we're working towards getting, everyone to understand how this works, this next slide then shows everything all encompassing. So here, as you can see, here's where Waldo is, and I cut him out and everything else is isolated. If we go back to the original image, you can see here, Waldo actually is here. But like I said, because I moved the canvas around in this big yellow background, you couldn't pinpoint where Waldo is if you were working off of the previous image I showed to you, right? So again, here is Waldo, and now we know where Waldo is and we can move on. So what are the branches of zero knowledge proofs? So we have zk-SNARK and zk-STARK. So we'll get into those right away. So what is a zk-SNARK? A zero knowledge SNARK is a zero knowledge succinct non-interactive argument of knowledge. It's a tongue twister, eh? So what exactly does that mean? Again, we'll get into all of that. What does that mean here? A zk-SNARK allows you to generate proof that some computation has some particular output in such a way that the proof can be verified extremely quickly. The key word is extremely quickly, and that is why SNARKs are succinct, because they can be verified quickly as opposed to STARKs. We'll get into all of that, but the selling point primarily with SNARKs are the ability of them being verified extremely quickly, right? So what is a zero knowledge STARK? Zero knowledge, scalable, transparent argument of knowledge. A zk-SNARKs are built with scalability in mind, as well as the resistance of attacks from quantum computers. They're similar to SNARKs as they prove a computation without revealing its data. The proof sizes are larger than SNARKs, which puts the scalability to question. So SNARKs are relatively small in terms of proving their size, their transaction size, and proving the computation. SNARKs are smaller, which means you're able to process a lot more, and they probably require a lot less computing power as opposed to STARKs. To be fair on STARKs, though, they're fairly new, and I personally am optimistic at the fact that the more this technology is refined as time progresses, the better it is, and you could say the smaller the transaction and the proof size of STARKs will get. But that being said, let's look at some of the differences between SNARKs and STARKs. So this is a handful to take in, but we won't be going through every single thing. There are 2 points I just need to point out. Size estimate for one transaction. These are SNARKs. SNARKs are about 200 bytes per transaction, as opposed to STARKs that go all the way to 45 kilobytes. We're going to ignore bulletproofs because we're not going into those in this video, but you can research and learn more about bulletproofs. They sort of actually work in conjunction with SNARKs, and if you're curious, you can learn about that. However, the proof sizes of STARKs are 45 kilobytes as opposed to 200 bytes in with SNARKs, and that is a massive difference. There's 200 bytes on SNARKs and 45 kilobytes on STARKs. But as we can see here, size estimate for 10,000 transactions. TX is still 200 bytes on SNARKs, but the key here says about 500 gigabytes. I'm not entirely sure what this number means. However, when we look at STARKs, it is about 135 kilobytes. My theory is that as STARKs will be a lot more useful when there are a lot of transactions happening. And when there are that many transactions happening, the sizes are not overwhelming because they are fairly consistent, as opposed to SNARKs where we aren't entirely sure what's happening. So again, you can go through all of this. The description, the link to these resources will be in the description below. Again, more differences. Proof size of SNARKs, 288 bytes. STARKs go all the way to 200 kilobytes. The time, STARKs are faster, approval time, and as you can see here, verification time, SNARKs are about 10 milliseconds. So SNARKs are verify transactions and computations rather quickly. 6.6 milliseconds faster than STARKs, and well, ridiculously faster than bulletproofs. So why do we need zero knowledge? This is very important, and why do we need it? Why do we bother with this technology? Why? Let's get into that. First thing is privacy. Having all of your data out in the open blockchain is no fun. Quite frankly, it isn't. I remember when I started geeking about, crypto and blockchain and all of that cool stuff. And one of the selling points with the blockchain was its transparency of data. And a lot of people, were geeking over that. And I thought about it, and it wasn't a very deep thought, but it was interesting to think that if every single transaction is public on the blockchain, that doesn't seem very safe. However, zero knowledge proofs come in to abstract away certain piece of data that should not be made public, like your identity, your date of birth. We get to have the opportunity to choose certain piece of data that we want to make public and the ones that should be made private, as it should be. So privacy is very, very important. It's ridiculously important, and in a decentralized manner, way more important in the blockchain. So zero knowledge proofs are solving that, and I'm super excited. Second reason we need zero knowledge is for scalability. With this, we're able to, you could say, outsource, right? We're able to outsource certain transaction processes. We're able to outsource certain transaction processes off chain, batch them into a single transaction, and send them to the main chain. This is so cool. So here's where this really cool diagram comes in that I'm going to show you in a bit, right? So zero knowledge rollups, because anything that is sort of scaling Ethereum, because now we've moved into the blockchain, scaling Ethereum is a rollup. Zero knowledge rollup operators submit a summary of the changes required to represent all the transactions in a batch, rather than sending each transaction individually. A handful, a mouthful. Here's what it simply means, right? Essentially, here we have a lot of batch transactions. Let's say these are 10,000 transactions that a zero knowledge prover has proved off chain, verified. We've carried out all of these transactions, and then we're sending them to the Ethereum virtual machine. This significantly reduces the pressure that the Ethereum virtual machine and the Ethereum blockchain, would otherwise need to process all of these transactions, because they've been batched together, and all a zero knowledge proof is sending is the proof of those transactions, right? That those transactions are actually accurate. So Ethereum virtual machine just has to process a single computation, as opposed to processing 10,000 computations at a time for every single transaction. That, obviously slows down the blockchain, and we know Ethereum has its issues. But with zero knowledge, we're able to scale really fast. So here's exactly how that works. So the prover here has a batch of transactions, and it sends it to the EVM, the verifier. So the verifier verifies the transaction, right? And then it creates a new block, and then it sends that into the Ethereum blockchain, which has been verified, and that gets added into the blockchain and repeats itself. It repeats itself. It repeats itself. So again, the prover sends a batch of transaction, the proof of transaction that it has verified to be true. And again, with our definition, the transaction has to be honest. Proof of transaction, they verified and everything, the verifier verifies the transaction, the computation seems good, creates a new block and sends the new block into the Ethereum blockchain, and things progresses, and Ethereum is able to process a lot more transaction. The throughput of the transaction that are being processed are a lot higher, and that is really cool. So, and then everything, sort of all of these processes just yields to this single block, which is sort of like what we have here. Every single one of those processes yields to a single block in the Ethereum blockchain. So who are the folks that are building on and with zero knowledge? We have Mina, the world's lightest blockchain. They are primarily using the zk-SNARK technology. We have zk-Sync, a layer 2 scaling solution. They are doing really cool stuff. They've been working in development for over 4 years. So, and they just went on the mainnet a couple months ago. So this should be interesting to see what they have going on. We have StarkNet. StarkNet is a permissionless L2 zk-Rollup. They are working with the zk-SNARK, which is interesting. It's cool. We have some people building with SNARKs and building with STARKS as well. And then Polygon zk-EVM. zk-EVMs are very interesting. We won't be talking about them in this video, but they are a different way to think about scaling Ethereum with zero knowledge. So yeah, so these are the folks building with and on Ethereum. I will be making a handful of videos on Mina because they have like zk apps, I think they are called. So I will be making a handful of video going over how those work and the tutorials and building dApps with the zk apps. And so stay tuned if you're curious about learning how to build on Mina protocol. So that will be happening as soon as possible. And so thank you so much for stopping by and learning about zk with me. I have been, again, like I said, geeking over this topic and just learning as much as I can. This has been fun. I hope you found this video helpful. There will be timestamps and you can sort of like learn at every point and go back to every point in this video and learn stuff. So this has been really cool. Thank you again for watching. If you found this video helpful, please give it a like and subscribe and share with your friends who are curious about learning about zero knowledge like I am and like yourself. And until then, I will be seeing you next time. Thank you for watching. Have a great day and take it easy.